Molecular property predictions. What does it mean? So we have a molecule and I have a property of interest. And what I want to do is, I want to use this molecule and see whether it has a desired property of interest. Now for that, what I have to have is a molecule which I can actually convert into molecular graph. And for each of this molecular graph, I have a set of features. In this particular example, if you can see that I have atoms as my nodes, and if there is a bond between them, I have put an edge between those two nodes. Here we have not considered hydrogen atoms, and that is typically done in many molecular graphs. Here, if you can see, I have three kind of atoms or nodes. I have an atom nodes describing C, I have a node describing N, and I have a node describing O. And associated with each of this node, I have corresponding feature vector of the same length. Now, what I'm interested in is, given this molecular graph, can I predict a property of interest? What I have to do is, I have to actually train a graph neural network which takes this molecular graph with the feature and generate a representation of this particular graph. This is graph representation. This particular feature vector is actually obtained through graph neural networks. Underlying graph neural networks can be anything. It can be GAT, it can be GCN. Once I have a graph representation, what I'm going to do is, I'm going to use some other neural network. Here I'm using feed-forward neural networks to predict the property of interest. In this particular case, in a molecular property prediction case, what we have is a very interesting problem from the machine learning point of view. Historically, I have historical data where I have a molecular graph and associated property of interest P. So I have, for each graph, I have this P, and let's say I have certain data sets which are. Now, remember that for all the molecules, I do not have this property of interest Pi. And in fact, in practice, this N is quite smaller number compared to the molecules available to us. Let's say there is around L number of molecules known to us, then the L is going to be very, very, very higher than the N. Hence, what we have is, we have historically labeled data, which is very small. However, we have a huge amount of unlabeled data. Which is a molecule available to us. There are different databases in which these molecules are actually available. Some databases are 2 million molecules, some databases has 100 million molecules. And most of them are available freely for a non-commercial approaches most of the time. Now, what we are having is the problem where we have a lot of unlabeled data and few labeled data. In that case, the question in the molecular property prediction people often ask is, can I use this unlabeled data to actually get a better feature representation or graph representation from the graph and the feature associated with it? Because this particular model can use all the data available, labeled plus unlabeled data, to generate a better graph representations. Once I have this graph representation, I can use this labeled data at this particular stage and build a model. Remember that I'm using here neural networks model. You can use any other model, any supervised learning model, depending on the task. It can be classification task or it can be regression task. So depending on that, you can use any other model. I have used feed-forward neural network. And once I have learned this neural network, what we have to do is, for a new unlabeled molecule, I have to go through this one. For new molecule, I have to go unlabeled molecule. I have to go through graph neural network, generate a graph representation, and then use this model to predict the property for this unlabeled molecule. And that's what is a molecular property prediction task is all about. Given a molecule, want to predict a property prediction using a graph neural networks and feed-forward neural networks. Now, if you recall, we have studied a message passing neural network, MPNN, and this is one of the widely used molecular property prediction deep learning approaches. Here, we typically use each node as an atom, associated features, and then age also we use when there is a age between two atoms in a molecule of interest. Once we have that, we use three-stage approaches, where in the first two approaches, there's a message is passed from between two nodes in the graph, where message from neighbor for the ith or vith node is basically summation over all the nodes in the neighborhood of vi, where for the message function which takes feature for ith node, feature for all the neighbor node, and if we have age feature available, it will take age feature is also as the input and generate the message from neighborhood node, and then it will actually use the previous feature and a new message to update the current feature using the updation function. Remember here that this particular task of message passing is done for several time instances. For example, 10, 20, 30. And after that those time instances, or let's say chosen time instance, T, we are going to actually freeze our feature associated with the particular node, and then we perform a property prediction, which often is called readout stage where we read out function R is going to use feature associated with ith node, and for all the nodes in a feature associated with the feature associated with the ith graph, so all the graph, and perform the property prediction task. There will be in readout, before readout function slowly, there will be an aggregator function depending on graph related property or node related property. Okay, so in a molecular property prediction, there will be aggregators which will take this updation feature, create a feature vector for out, and during the readout stage, it will predict the property for that particular molecule. Now, if you look at it here, the age features have not been used actively. And people have shown that age features can be useful, or in fact, instead of using the message passing between nodes, can we do with the age would be a better option. So direct message passing neural network, which is called DMPNN, its filter updates its features of age and nodes, where direction of message matters. In other words, going from the message from V to W and W to V are different. Here we are passing feature between two nodes I and J, or Vi and Vj, where the HT is a age feature, message function M is always there, and what it does is actively takes the feature of node I and remaining node in a neighborhood of I, with except Vj, and construct the message from the neighborhood for next instant t+1. Once it has it, it will actually update the feature vector for age, which is, you can see HT is becoming HT+1, and once it has it, it will create a message for ith node by summing over all the age features. And once we have this for the ith node, we'll construct new feature Hi by concatenating the old feature Fi and Mi, and construct the Hi for the ith node. And theta here is the parameters of interest. Once we have this Hi, we can actually, by summing over all the nodes in a G, we can construct feature for graph G, which is the feature vector for the molecule. Hence, in a direct message passing neural network, we actively use age features as well as direction of representation, and we update our message to the ith M and then get a HI, and then sum over all the HI to get a feature vector for the molecule. In one of the paper where DMPNN has been proposed, they have used several node features like atom type, number of bonds, formal charge, integer electronic charge assigned to atom, chirality, number of hydrogen molecules it is been bonded with, hybridization, aromaticity, atomic mass. For the age features, the bond type, conjugated or not, in the ring, etc. have been used as the age features. Using these two, they have applied DMPNN and compared with the base models on the benchmark datasets. So MolNet provides you a set of benchmark datasets on which you can actually try out your algorithm and see whether it outperforms some of the base models at that time or state-of-art models. So if you develop a new graph neural network algorithm or any approaches to perform a molecular property prediction task, what you can do is you can actually go to MolNet, look at these data sets, which has two kind of problems, which has a set of classification data sets as well as regression data sets. And here they have actually compared the DMPNN based feature engineering with MolNet based model available. And you can see that in a classification task, most of the classification tasks, DMPNN performs better than MolNet based model. In certain tasks, it performs worst. However, in certain tasks, it is marginally poor. So in a classification, the DMPNN performs well on an average, we can say that. And there are different kind of property. For example, HIV datasets, TOX21, they look at a different aspect of the molecular property predictions. Similarly, they have also looked at for the regression task, and you can see that it performs far better than MolNet based. While in some of the tasks, it is marginally poorer than the MolNet based. And hence, we can see that the DMPNN provides quite interestingly better feature engineering of the molecules and outperforms the best model in a MolNet. Of course, this publication has been in 2019, and after that, in last 3.5 years, there are more and more better models have come who can actually outperform the DMPNN. But the point here I want to make is that representing molecule as a graph as a definitely advantage. It definitely provides a better feature engineering. And also, in future, the different formulation of graphs can be used to actually outperform the DMPNN or other models for the property prediction. The next applications which I'm going to look at is a protein interface prediction. What does it mean by protein interface predictions? So all of you know that protein are chains of amino acid with functions. There are protein functions. It is each of these circle, you can think of amino acids which are actually connected together to create a protein. and this protein has a certain functions. There are around 20 amino acids, and it vary between 20 to 22. And amino acids are also a molecule. An amino acid is nothing but a molecule. It's an organic compound, as a matter of fact, and hence we can think of individual amino acid, as a converting as in a molecular graph. Typically, these proteins, they functions through interaction with other protein and leads to a certain kind of functionality, which has a biological importance. And finding site of interactions or interface is an important and challenging problem in the field of biology and often drug discovery and drug design. What does it mean by protein site of interactions? It means that two amino acid residues from different protein interact or not, and because remember that protein is set of amino acids. So here the interest is, given protein pair of amino acid residue, we want to predict whether they interact or not. So let's look at more systematically. Here what we can do is we can actually model protein as a graph with a G, with a V as a vertices, E as H. What is a set of nodes, which is V? It describes each amino acid residue in the protein of interest. What is E? It describes a set of edges describing the spatial distance between atoms of amino acid residues. Typically, we take a K closest amino acid residues determined by the mean distance between their atoms and construct the edge between those atoms of those amino acids. Node features can be taken as a properties of residues, amino acids, and edge features in certain publications. They have taken distances and the angles between different residues. And this is one of the publications which actually use these properties. So what we'll do is, we have to now perform or formulate a protein interface prediction task problem using protein graphs and given node or edge features. Now, a pair of amino acid residues from ligand protein or protein 1, which is described again by a graph, and receptor protein, which is again described by the graph, which is GL and GR. GL belongs to ligand protein, GR belongs to receptor protein, and associated set of nodes and set of edges are described as a VL, EL, and VR, ER. And task, as I mentioned, whether these two residues are in the protein interface or not. So I'll take this residue, which are nothing but vertices of graphs of ligand protein and the receptor protein. And based on that, these vertices we want to actually classify, which will be a binary classification because we are having either 0 or 1 corresponding to protein. They are in a protein interface or not. So using this binary classification problem, what we can do is we can solve protein interface prediction problem. So let's look at the ligand graph. So it is a graph, as we discussed, with set of nodes and set of edges and node features. For a while, I have assumed there are no edge features. However, if there are edge features, we can also use some of the techniques which we have used. For example, message passing neural network or directed message passing neural network. And you will see how we can use it. Similarly, we have a GR, which is a receptor protein graph associated with different features. Remember that this both can be a different kind of graphs depending on the protein. And the features you can see are given here. What we are interested in is seeing there whether this node VR and node VL leads to an interaction or not. So what we will do is we will actually perform a graph filtering operations on this particular graph and also on GR graph. So we are going to perform graph filtering operations on graph GL as well as graph GR independently. Recall that what we are interested in is interaction between VL and VR. In other words, I'm interested in looking at filtering operation, or I'm interested in node features related to two different graphs, but node features. And that's why we are going to use only filtering operations, no pooling operations. I'm not interested in graph related properties. I'm interested in particular node in a one graph interaction with a node in another graph. So I have actually done graph filtration operation and I achieved filtered node features. If I have done good job in graph filtering operations, I should have a better feature representation for this node and better feature representation for this node. So I have a feature representation for VL and VR. This is the after my graph filtering operation. These are the new features vector. What I'm going to do is I'll take these two features and perform the merging operation and create a merged feature for these two nodes or pair features, I will call it. Once I have these pair features, I will take these features and with available data, of course, I should have a protein interface prediction data set where I have label data where set of amino acid residues are interacting in the proteins. So using that particular one, I will generate a classification problem and train fully connected layers or full feed forward neural network to perform a classification task. Recall that in certain application, this complete task is done in a one go. It means that learning happens, all the parameter learning happens throughout from the classification to graph filtering operations. Sometimes we can decouple it. If we can first learn features for each nodes and then merge them and then independently learn the classic feed forward neural network to perform the classification tasks.